So now in this lecture, I will prove the Hahn-Banach theorem. Which is also based on Zohn's lemma. So in order to state the theorem, I need some definitions. So in this lecture, I will always be working with a normed linear space, actually, over the real numbers. So the field will be the real numbers. And so I have a functional L, which is defined in X, takes values in the real numbers. I will say that it's linear if for all x and y in X, for all alpha in R, I have that Lx plus y, it's equal to Lx plus Ly, and if L alpha x, it's equal to alpha Lx. Now, the main theorem will be an extension, so I will assume that I have a sublinear space, and that that I have a functional which is defined on this sublinear space, and I want to extend this linear functional to the whole space. So the theorem, the Hahn-Banach theorem, is as follows. So I have a linear space X. I have Y, a sublinear space. And on Y, I have a linear functional. So what I want, so what this means is that for all x, y in Y, and for all alpha in R, these two properties are defined. And what I want is to extend this linear functional to the whole space X. So I want to define a new functional, which is linear, satisfy these two properties, which is defined on X, and such that, well, if I take a point in Y, the value of this new functional coincides with the value of small l. For that, I will need an assumption. So I'll say, I'll assume that there exists P, which is defined on the whole space. So in contrast with L, P is defined in the whole space. And P, well, it's not linear, but it satisfies two properties, which I write here. First, it's positive homogeneous. This means that P alpha x, it's equal to alpha px for all x in X and alpha positive. So it's positive homogeneous because here I'm requiring data identity only for positive alphas. And then the second condition, it's that P is subadditive. Which means that Px plus y, it's less or equal than Px plus Py for all x and y in X. Well, a clear example of a functional P from X to R which satisfy these two properties is the norm. So if X is a normed linear space, you can define Px just as the norm of X, and you see that, well, if you take the norm of alpha x, for alpha positive, this is exactly alpha times the norm of X, and by the triangle inequality, the norm of X plus Y, it's bounded by the norm of X plus the norm of Y. So this is an example. There are many others that will appear in these lectures. So I'm assuming that there exist these functional P defined on X, which is positive homogeneous, sub-additive, and such that, so the main condition is that Lx, or no, it's bounded by Px for all x in y. So you see, L is defined only on y. So in that condition, I'm requiring this bound only for the points x in y, because L is only defined on y. And so this is the assumption, the main assumption. So we have L, which is defined on a sublinear space. L, it's linear. It's bounded by a functional which is subadditive and positive homogeneous. And the statement is then, if these conditions are matched, then there exists a linear functional L, which is defined on X, and, well, with three properties. L is linear, so we want to keep the linearity. L, it's an extension, so L of y, it's equal to L of y for all y in y. And L remains bounded by P. So what, under these assumptions, we can prove the existence of a functional L defined on the old space. So it's linear and it's an extension. So it's an extension of this linear functional small l, and which is still bounded by Px. So this is the statement of the Hahn-Banach theorem, and I will prove the Hahn-Banach theorem based on the zone lemma in this lecture. So here's the proof. And remember, I didn't insist on that, but I'm assuming that X, it's a linear space over the field of the real numbers, right? Because I'll be using less or equal, so I'm considering the field as the real numbers. So the proof, well, the proof is divided in two parts. In part one, which I will present now, what I will do is I will extend my functional L to a further dimension. So I assume that y it's different from x. So that y it's a proper subspace. So this means that there exists a z which does not belong to y. Now I consider a new space, yz, which is the space composed of all elements which can be written as a linear combination of an element of y and a scalar multiplying z. So this is y in y and alpha in r. So this is my space yz. It's clear that y is linear. If you take yz, it's linear. You take 2 points in yz, you sum them up, you get a new point in yz. If you multiply that by a scalar, you get a new point in yz. And also, what I claim is that y and alpha are uniquely determined, which means that if you take a point in yz and you write it as y plus alpha z in two different ways, well, they have to coincide. So if I take y1 plus alpha 1z equal to y2 plus alpha 2z, what I claim is that y1 it's equal to y2, and alpha 1 it's equal to alpha 2. And why is that so? Well, because it follows from this identity that alpha 2 minus alpha 1z it's equal to y1 minus y2. So this is an element of y. And since z doesn't belong to y, by assumption, the only way in which I can make this expression to belong to y is to make alpha 2 equal to alpha 1, so that this is 0, and 0 indeed belongs to y, because y it's a linear subspace. So this implies that alpha 1 is equal to alpha 2, and if alpha 1 is equal to alpha 2, well, you can cut these two expressions and get that also y1 is equal to y2. So this representation of elements in yz is unique. Now L is defined on y, and I want to extend its definition to yz. So I have to define L of y plus alpha z. But I want L to be linear. So L to be linear means that this is equal to Ly plus alpha Lz. Well, y belongs to y, and I want L to be an extension. So this has to be equal to L of y plus alpha, and then let me represent L of z by a. So this is a number, so this is what I have to determine in order to define L in yz. If I determine a, then I can tell you what is the value of L of any point in yz. You take any point in yz, it can be decomposed in this way. Its decomposition is unique, and then for L of this point has to be equal to L of y plus alpha times this value a which you fixed. So this has to be the definition of capital L on yz if I want L to be linear, capital L to be linear, and to be an extension of small l. Now I have a third property which I want to keep, is that L of any element of this point, so L of y plus alpha z, has to be smaller. I want, the third property is that this inequality, it's valid for all points in yz. Well, so this will give me the restrictions on the value of a. I have to check whether it's possible to to set a value for a in such a way that this inequality is satisfied. But what is this inequality telling me? This inequality is telling me that let's see, that if alpha is equal to 0, this is always satisfied because I know that this inequality, well, L on y coincide with L. So if alpha is equal to 0, this is just small l of y, and small l of y, it's indeed less or equal than p of y. So I can take alpha non-zero. So let me first consider the case in which alpha it's strictly positive. And for that inequality to hold, in view of this definition, what I need is that L of y plus alpha a, this has to be equal, smaller or equal than p of y plus alpha z. And well, this tells me that alpha of a has to be smaller than py plus alpha z minus L of y. Alpha is positive, so I can divide that by alpha on both sides. L is linear, so I can place the alpha inside L. Now I can use the fact that P is positive homogeneous. Since alpha is positive, I can insert alpha inside P, and this gives me that P alpha plus Z minus L of Y alpha. And this has to be satisfied for all Y and all alpha positive. But, well, since I'm taking all y, this is, I don't care about alpha, this is satisfied if and only if A, it's less or equal than P of y plus z minus L of y for all y. Right? I need this inequality to be satisfied for all y and alpha. I'm now concentrating on all alpha strictly positive, so this has to be satisfied by all y and all alpha strictly positive. But, well, this means that this inequality has to be satisfied for all y. Fine. But, so, if I want L to be satisfy this inequality, note that I cannot choose A in any way. I have to choose an A which satisfies this inequality for all A. So that means that A has to be less or equal than the infimum over all y. So I need A to be less or equal than the infimum over all y of py plus z minus ly. Now, what happens if alpha it's negative? Well, this means that I want minus alpha to be positive. So I want this inequality to be satisfied, but now I'm taking alpha negative. So this means that Ly minus alpha require this for all alpha negative, the same thing of requiring this for all alpha positive. Right? Asking that for all alpha negative is the same thing as asking this for all alpha positive. Now I can repeat the same argument, and by placing minus alpha A on this side, I get that alpha A has to be larger or equal than Ly minus Py minus alpha z. I divided all terms by alpha. Now this has to be satisfied for all y in y and alpha positive, but this is satisfied if and only if we have the second inequality that Ly minus Py minus z is less or equal than A. So what I'm meaning is that if this is satisfied for all y and all alpha, it's certainly satisfied for all y. And if this is satisfied for all y, this one is also satisfied for all y and all alpha positive. Therefore, we have two bounds for A. We have a lower bound for A, and we have, so A has to be larger or equal than the supremum, and A has to be less or equal than the infimum. But assume that, so now suppose that indeed the supremum of Ly minus Py minus z for y in y, assume that this supremum is less or equal than the infimum, which is written over here. So that's Py plus z minus Ly. Assume that this supremum is smaller than this infimum. I still need to check if this is the case, but assume for one moment that this is indeed true. This means that I can choose A between this supremum and this infimum. So choose that A. Once you choose that A, define capital L by this formula. And it turns out by the computation we just did that this inequality holds. That indeed for all alpha and all y, we have this inequality. Which means that we were able to extend our functional small l to the set yz through this formula. So let me repeat. Assume that this supremum is bounded by this infimum. If this is the case, it's less or equal. I can always choose one point A. I can choose one A in this interval, in which the left boundary is this supremum and the right boundary is this infimum. If these supremum and infimum are different, I can choose any point in between. If they are equal, I have to choose that exact value. But in any case, I can always choose A in between if we have this inequality. Then I insert this A in this formula. The L I obtained is linear. It's equal to small l on the set y. And moreover, this computation we just did shows that L of y plus alpha z, so that L, this functional which is now defined on yz, still smaller bounded by p on the set yz, because A has been chosen for that to hold. So what remains to be done in order to show that indeed we can extend the definition of L to this space? It's to prove that this inequality holds. So I will erase everything and show to you that indeed this inequality holds. So I have to prove that for all y1 and y2 in y, L of y1 minus p y1 minus z, it's less or equal than p of y2 plus z minus L of y2. If I can show that this holds for all y1, y2 in y, I can take the supremum over y1 on the left-hand side, the infimum over y2 in the right-hand side, to get this inequality. But this holds if and only if L of y1 plus L of y2, it's smaller than p of y1 minus z plus p of y2 plus z. So let's prove this inequality. We have to prove this inequality for all y1, y2. Well, so this expression, it's equal by linearity of L y1 plus y2. Note that I have to be careful because L is not defined on yz. L is not defined for z. So I cannot insert here z because, well, I get a point in which L is not defined. But L is defined on y, and y1 plus y2 belong to y, so L is well defined for that point. And now I can use the fact that L on y is bounded by p. So by assumption, L is bounded by p1, py1 plus y2. Well, but p, in the opposite of L, p is defined on the whole space. So now I can introduce z in this equation by writing that p y1 plus y2, it's equal to p y1 minus z plus y2 plus z. I can introduce z inside in this expression because p is defined in all the space. And now I can use that p is sub-additive to say that this P of y1 minus z plus y2 plus z is less or equal than P y1 minus z plus P of y2 plus z. And this is exactly what we wanted to prove. So we just showed that this inequality, it's indeed in force, it holds, and therefore that we are able to extend small l to this space yz, keeping all properties of the linear function small l. So in the first part, what we proved is that if y is different from x, I can always extend L to, I take a point z which doesn't belong to y, and I can always extend L to the space generated by y and z, keeping all three properties we need, which means linearity, the fact that L coincides with the functional defined on y, and so that L is bounded by P. Now, in part 2, we will use zone lemma to show that this allows us to extend L to the whole space. So in part 2, I will introduce a new set, omega. Omega will be formed by subspaces. So let's say that Z and LZ. So Z, here it's a subspace of X, linear subspace, which contains Y. Then LZ, it's a linear functional which is defined on Z and which satisfies the three properties, which means that it's linear, that Lz of y it's equal to L of y for y in y. Remember that I'm assuming here in this set that Z contains y, so Lz is defined on y. And finally, that Lz of Z it's less than P of Z for all Z in Z. So this is my space. So the elements of this space are formed by a pair. The first coordinate, it's a linear subspace of X. And the second one, it's a linear functional, which is defined on Z. And it's an extension of Y, because it's equal to, it's an extension of small l, because it coincides with small l on Y. It's linear, and it's bounded by P. So this is my set. On this set, I will define an order. So I'll say that Z1, LZ1, it's smaller than Z2, LZ2, if Z1 it's contained in Z2, so the linear space Z1 it's contained in the sublinear space Z2, and LZ1 of Z it's equal to LZ2 of Z for all Z in Z1. So the second condition requires, so you see that Z2 contains Z1. So the second conditions require that LZ1 and LZ2, they coincide on the small space Z1. If these two conditions are satisfied, I will say that this element of omega, it's bounded by, it's less than this element of omega. Now I leave it to you to check that this relation is a partial order. And I want to apply zone lemma, so I have to check that what I claim is that the hypothesis of zone lemma is satisfied. So let me take a set omega prime, a subset of omega, which is totally ordered. So omega prime, well, will be formed by such elements. So this will be Z alpha, L Z alpha. For Z alpha, or for alpha, in some set I. So all points Z, LZ. So if I take a subset of omega, it's formed by such elements. You see that this is a linear subspace and this is a linear functional defined on Z alpha. Now I'm saying that this space is totally ordered, which means that if you take alpha different from beta, either Z alpha, L Z alpha, it's smaller than Z beta, L Z beta, or the opposite. So one of them is smaller than the other one, which means that either this space is contained on that space and this functional coincides with that functional on this space, or the opposite. Now I want to I claim that omega prime has an upper bound. I'm claiming that omega prime has an upper bound. And okay, so I have to construct this upper bound. And what will be my upper bound? Well, it has to be an element ZL. So let me define these upper bound, and I think now you know what the order means. So ZL will be, well, what is the linear space? The linear space, I'll take just the union of all Z alpha. So Z, so it's a pair. Z will be the union for alpha in I of Z alpha. And L, well, I will define L in the following way. Take Z in this very large space Z. I want to define L of Z. Well, since Z belongs to this space, it belongs to this union. Since it belongs to union, this means that Z is equal to Z alpha for some, I'm mixing things up. This is a linear space, so maybe not to mix, let me take an element of this space. This means that, so let me get back here 1 second. These are linear spaces. I'm taking the union of these linear spaces, and I'm calling this union Z. I'll show in a second that Z is a linear space. Now, the second element has to be a linear functional defined on Z, on this linear space. So take an element of this linear space. Well, since this linear space is that union, this means that W belongs to some Z alpha. Now I want to define L of W. Well, since W belongs to Z alpha, I will just take L of Z alpha, which is well defined, and set it L of W to be equal to LZ alpha of W. Of course, I need to show that this is well defined, because if maybe W belongs to a Z alpha and also belongs to a Z beta, that this definition maybe give me two different values, and I have to check that this is not the case, that this is well defined. So, but at least these are the definition I'm proposing. Let me show you now that everything is fine. So my first claim is that Z is a linear space. So a linear subspace of X. Well, any of these spaces Z alpha are contained in X, so the union is contained in X. So this is not a problem. What we really need to show is that it's a linear subspace. So let me take two elements, omega 1 and omega 2 in Z. Let me take a scalar, maybe let me call that theta, a real number. And I want to show that the addition belongs to Z and that theta times omega 1 also belongs to Z. Well, since omega 1 belongs to Z, it belongs to this union, so omega 1 belongs to Z alpha 1 for some alpha 1, and the same thing can be said about omega 2. It belongs to some Z alpha 2. Now, since this set omega prime is totally ordered, I know that either Z alpha 1 LZ alpha 1 is smaller than Z alpha 2 LZ alpha 2 or the opposite. Well, without loss of generality, let's assume that Z alpha 1 LZ alpha 1 is less than Z alpha 2 LZ alpha 2. Well, if this is the case, this means that Z alpha 1 is contained in Z alpha 2, which means that omega 1, which belongs to Z alpha 1, also belong to Z alpha 2. Therefore, both belong to Z alpha 2. Z alpha 2 is linear. This shows that the sum belongs to Z alpha 2, and Z alpha 2 is contained in Z, and therefore the addition of omega 1 with omega 2 belongs to Z. In the same way, since omega 1 belongs to Z alpha 1, theta is a real, then theta omega 1 belongs to Z alpha 1, Z alpha 1 is contained in Z, and therefore theta omega 1 belongs to Z. This proves that Z, this space which I just defined, is a linear space. Now, I have to show that this is a linear functional defined on Z. I already proposed a definition. You take an element in Z, it belongs to some Z alpha. Let me propose that definition for L of omega. Well, I claim that first it's well-defined, and then that it's linear. That it's well-defined, what may happen? Well, it may happen that omega belongs to a Z alpha 1, and it also belongs to a Z alpha 2. But if it belongs to Z alpha 1 and Z alpha 2, since one of the space is totally ordered, either one is smaller than the other, or the other is smaller than the first, so let's assume that this inequality holds. This means that Z alpha 1 is contained in Z alpha 2, but also means that on Z alpha 1, these two functionals coincide. And this means that L of Z alpha 1 or LZ alpha 2 of omega, they coincide. Because in our definition of this relation, I'm requiring also the linear functional to coincide on the smaller space. So I'm assuming here that this point, to show that L is well-defined, that the point belongs to two different sets, linear subspace. If they belong to different linear subspace, since omega prime is totally ordered, one is contained in the other, say Z alpha 1 is contained in Z alpha 2. Moreover, LZ alpha 1 coincide with LZ alpha 2 in Z alpha 1, and since omega belongs to Z alpha 1, these two values coincide, and therefore L is well-defined. In the same way, we can show that L is linear. Take omega 1, omega 2 in Z. This means that omega 1 belongs to some Z alpha 1, omega 2 to some Z alpha 2. Assume that Z alpha 1 is bounded by Z, it's contained in Z alpha 2. This means that both alpha 1 and alpha 2 belong to Z alpha 2. So L omega 1 plus omega 2, by definition, it's equal to LZ alpha 2 omega 1 plus omega 2, because omega 1 plus omega 2 belongs to Z alpha 2. By linearity of L Z alpha 2, we get that L of the sum is equal to the sum of the L's, and from that identity we get the linearity of L. The same argument can be extended to multiplication by scalars. It's even easier. So with that, we proved that L is linear, Z is linear subspace, which means that the pair Z alpha, so we just proved that the pair Z L, it's an element of omega. Right? Omega, or the space of pairs. Now, I want to show that ZL, it's an upper bound. So I want to take any element in omega prime and show that this element of omega prime, it's bounded by this one. So take an element of omega prime. It's a pair, Z alpha, LZ alpha. Well, I claim that Z alpha is contained in Z. This is clear from the definition of Z, because Z is the union of all of them. So Z alpha is contained in Z. And I want to show that L, it's an extension of LZ alpha. And indeed, in the way in which we define L, on Z alpha, L and LZ alpha coincide. So L coincides with LZ alpha on the space Z alpha. Therefore, this is an extension. I'm just realizing that I proved that L it's linear, that L it's an extension, but I didn't prove this inequality. The third inequality, it's also very easy to prove because L coincides with LZ alpha in Z alpha, and LZ alpha it's bounded by P on Z alpha. So by definition, Z will be bounded by P on the space Z. So this proves that ZL, it's an upper bound for that we just constructed. It's an upper bound for the space omega prime. So the hypothesis of zone lemma is satisfied. We consider a totally ordered subspace of omega, and we constructed for that totally ordered subspace a point in omega which is an upper bound. So we can apply zone lemma, and zone lemma tells us that there exists a maximal point in the space omega. So I will erase everything and just keep the fact that omega, defined in this way, has a maximal point. So we just proved that this set omega has a maximal point, which I'm representing by Z LZ. And now what I claim is that Z has to be equal to X. Well, you see that part 1 and part 2 of my proof were completely independent, right? I never used part 1 in the proof of part 2, and of course I didn't use part 2 in the proof of part 1. They are just independent facts. Now, I claim that Z is equal to X. And why is that so? Well, if Z it's not equal to X, now I can apply part 1, and I can find W, which does not belong to Z, define the space ZW, which is the space in which I consider all points which can be written as linear combinations of a point in Z and W, and extend L to, and find LW, which is an extension of, which is defined on ZW to R. So what I claim is that this ZW, LW, now it's an element of omega. Well, this is what part 1 tells me, right? Part 1 tells me that since LZ satisfies these three conditions, the new LW, which I constructed in part 1, also satisfies these three conditions. And therefore, ZW, it's a linear space, subspace of X. LW, it's a linear functional, which is an extension of L, and which is bounded by P. So this point, ZW, belongs to omega. And this point, it's strictly larger than the point ZLZ. Right? Because, well, this set, it's larger than that one, and this functional coincide with LZ on the space Z. So indeed we have, they are different because this space is strictly larger, so they are not equal, and therefore this contradicts the fact that ZLZ is a maximal point because we just obtained a point in omega which is larger than this point. So we get a contradiction if Z is not equal to X, and that proves that Z is equal to X, and if Z is equal to X, we completed the proof of the theorem because this is exactly what we wanted. Z is equal to X, so we have a linear functional which is defined on X, which is linear, which coincides with L, small l in Y, and which is bounded by P. This was the statement of the theorem, and with that we complete the proof of Hahn-Banach theorem.